All right, so first up we have Peter Geissert talking about metadata-driven data science.
Thanks. All right, hello. Thanks. My name is Peter Geissert. I work with the Oregon Emergency Medical Services Program, and I wanted to talk to you a little bit about some work that we've been doing around using our metadata to drive our analytics and our work in the program. So first off, I wanted to acknowledge a few people and organizations. Oregon Emergency Medical Services Program personnel and data team meeting members, past and present, a lot of whom are in the room. So thank you to all of you. And to the Oregon Department of Transportation and the Traffic Records Coordinating Committee for partial financial support of this work. So in terms of what I'm going to talk about today, first I'm going to introduce what I see as the public sector quandary, and in particular in public health, the way we've worked with data in the past, and as we're in a transition to how we want to work with data in the future, and the limitations thereof. And then a very brief introduction to metadata and metadata-driven data science. And then an example that is a shaved little slice that can be fit into 15 minutes, pulling a one-to-one table from our database and the workflows there. So there are some recent trends in public health data science, EMS, and trauma that have a real impact on the work that we're doing. One is increasing opportunities for quality assurance and process improvement. And then public health modernization has brought all these expectations that our work's going to be data-driven. And then there's greater visibility of data science as a discipline, which is driving data literacy and a greater demand for data. And our data systems have expanded in coverage, and that makes the data that we have much more useful. So all of that is adding up to what I like to refer to as Potemkin Village data science. And this is basically a reference to the Empress Catherine II of Russia wanted to visit Crimea, and her field marshal had all of these portable buildings constructed that could be stood up and then taken down and then carried down the river and put up again to make it seem as though the region had these thriving communities and so forth in order to impress her. And historically, the approach to data in public health has been very much analyst driven, right? Analyst builds out a project, writes the code, builds reporting or visualization tools that are very specific to that project. And then over time, that has to be updated and maintained, right? So the issue is, right, that behind that facade, there is somebody in a hamster wheel, many of us in this room have probably found ourselves in these types of situations, trying to generate the data that's needed and stand it up to support those dashboards. And as the number of projects increases, the amount of work to support that increases dramatically. And so if you move from 1 to 2 projects, that's not necessarily such a big deal, but if you're talking about dozens or even hundreds of projects, we want to work smarter. So the goal here is to get upstream. We often talk about upstream in public health, right? But managing this situation and getting upstream of it really means working with our metadata. So what is metadata? And forgive me, I know this is a more technical room than I often present this slide to, but this is a book of poems by Shelley that belonged to my grandmother. So if we think of the poems as the data, here are some examples of metadata, right? The book plate will tell you where she went to college, right? And what her name is. Publisher information, table of contents and index, right? Things that are telling you where did this book come from and giving you information about how to read it and interpret it. Bookseller's marks written in pencil on the front page. Where on the cover, spine, and page will tell you, has it been left open? Has it been stored vertically or horizontally on a shelf? Was it in the sun, right? And then if we step back, right, we can talk about the dictionary of the language in which the book is written. We can talk about the grammar and the syntax of the language, right? So this is all metadata. And as we move to our data sets, right, there are many types of metadata. And I'm not going to go fully through this slide, but today I'll be talking a little bit about structural metadata and descriptive metadata. Basically, what is in our data sets and how is it stored? Where is it stored in our databases? And why do we need to do this? I often say a data system isn't software, right? Because oftentimes people think they're buying a data system, right? And no, the software is a substrate, right? The data system is an abstract, right? It's an organized collection of symbols and processes to operate on them. So a data system really preserves the structure of the real world system with some loss of information, right? And that correspondence is what allows us to use data sets to reveal things about the world. So an entity to a set of tables, a row to an occurrence, or a column to a construct or a data element. And that network of relationships is encoded in our metadata, which makes it highly useful for our purposes here. And so this is just a narrow slice of our EMS data set, right? We have the elements of the episode of care, right, corresponding to tables, and those tables are connected by keys. And of course, this is dramatically oversimplified. Some of these things have a whole cluster of different tables. Some of them are one-to-many and so on and so forth. But this is the general concept and feeding into the example that I'm going to share. So the concept here is we can design our workflows so that we update the metadata repository, right? The data dictionary on steroids. And these changes will flow downstream to all of our projects. And the generic functions that we use, they'll be built to take in the metadata tables as inputs, use them to extract data, analyze, and interpret it. And then the functions can be updated in one place only. And this is really a preparatory step to full automation of our reporting and dashboard work. Initial investment upfront, but overall, over the long term, there's going to be an ever widening gap representing time savings. And this is something that can potentially make it possible for small teams like ours to manage the demand, which is constantly growing. So the example, querying a database is an excellent use case for this kind of workflow, because if you're hard coding the table names, the element names, and you're doing this for dozens of tables for many, many projects, and you're updating continually over time. And I would like to actually address one of the slides that I deleted from this presentation in order to shave off some time from it. One of the things in our environment is that we have national data standards that are being updated on the regular, right? So our metadata has to change, right? And then you have to go through and refactor your code to account for those changes. So that becomes important here. But if you're doing this for many, many projects and updating continually over time, it is time to build a function. So here is, and don't worry about the specifics here, because we're going to go through this line by line, but I generalized the problem this way. And basically this function creates appropriate defaults and takes structured arguments and builds the database query. And this one's called extract DB table. And then here is a wrapper function that pulls in descriptive and structural metadata from our data dictionary tables. It creates a set of intermediary objects in the environment, and then it passes those objects to the extract DB table function, which sends the database query. So in order to deconstruct this, I'm loading a couple of things into my environment. I have a database connection, trauma DB object, a data dictionary, trauma DD, a crosswalk, which maps the relationships between the tables and the keys that connect them, called trauma CW, and a table name. The example I'll be providing is the blood gas table, which is in our trauma data set. So in production, there's a wrapper function that iterates through every one-to-one table and every one-to-many table, but we'll just be looking at this one. So The first step takes our data dictionary table and it filters it down to only rows where the table name is equal to the table name value in our environment. In this case, the blood gas table. So you can see here, I've got the table name column where it says blood gas. It's filtering down to only those rows. Then it's taking those rows, it's taking that subset of our data dictionary and ordering it according to a column called query order. This is, you can probably ignore this unless you use SQL Server, and then you probably know what the issue is. You have to basically put all of your long strings at the end of your query. And so this is the fix. So next, we're taking that subset of the data dictionary and we're looking for a schema name. So in our EMS data system, there are multiple schemas, right? So you have to provide a schema, but in the trauma registry, that's not the case. So in this scenario, it's looking at the schema, it's seeing that they're all in A, and it's creating a schema object in our environment, which is set to null. So this next step takes the table crosswalk and it filters down to the row that contains the blood gas table. The output's shown at the bottom. So what we have here is we have the names of each table, their correspondence, in this case 1-to-1, and the keys that link the two of them together. And we pull these three pieces of information out of the crosswalk. So first we're extracting the name of the source table. So this is the central table that establishes sort of the universe of records that we're pulling in. In this case, it's called the main data table, and it's been filtered down to the date range that we want. So the next piece is we're grabbing the key in that source table that we're going to use to link to this one. So we pull that key from the main data table. In this case, that's called the account number. In the trauma system, account number is the key connecting almost all of our tables, but this is very different in other databases. So while it seems like we could just say, match on account number, if we want to generalize this, we have to specify this for every example. So this is very different in the EMS system. The key is written into an object in the environment. And then last, we're going to pull the key from the blood gas table. So this is also account number, and we write this one to the environment. So now we're going to start using some of these intermediate objects that we've just created in the environment to extract a vector of keys that will be used to filter what rows we pull from the blood gas table. So up top, you can see we have the code from the function as it's written. And then below that, we see that what it gets translated into, right? So we take the source table name from our environment, main data, and then we pull the source data key column, which is account number. And the output is a vector called key list that contains account numbers from the records that are in the main data table. And that gets stored in our environment. So now we're able to take all of these intermediary objects and that we've created and pass them to the extract DB table function. So the database connection, which is called trauma DB object, is the first. And then the schema name, which is null. The table name, blood gas. The element list, which is the list of column names from the blood gas subset of our data dictionary. So every column we're pulling out. And then the key name, account number, and the value list, which is that vector of account numbers that was pulled from our main data table. So it takes all of that information and it generates under the hood, it's building a SQL query that goes to our database and pulls row level data for the patients of interest from the blood gas table. So the takeaways here, these functions are nested, and on that outermost circle, so here you can see extract all one-to-one tables. That's the one I mentioned that iterates through. And that one takes only 3 arguments. What's the name of your database connection? Where's your data dictionary file? And where's your crosswalk file, right? And all other arguments are created within the data pipeline as you move deeper. So these functions can be used equally with our Oregon Trauma Registry data or our Oregon EMS Information System, or IMSIS. These two databases have very different structures, The basic functions are agnostic to the database that they operate on, and all it requires is a properly formatted set of data dictionary tables. Other metadata-driven workflows are possible: updating and modifying repositories, extracting and updating documentation of value lists, constraints, and regular expression patterns that support data validation, functions to support automated update and deduplication. Some of the ones I'm really excited about, right? Data structures to store case definitions and denominator inclusion calculation for metrics, which Kavish, who's here in the room, is working on right now. Data set picker apps. This is probably one of the things that really drove this. Andy Nunes and I were discussing this several years ago and put me on this path. So cross data set mappings for metadata-driven approaches to automating data linkage. But what this allows is it has the potential to increase the capacity of small teams and low resource path out of the public sector quandary. I look forward to any questions you might have.
Wow, that was great to learn more about databases and how you're structuring that. All right, next up we've got Hanna Winter talking about introduce R to your other friends. I'll let her say the rest.
Hello, my name's Hanna Winter, and yeah, I'm here to talk about introducing R to your friends, or maybe it's introducing your friends to R. Your friends in this case being all the other programs that you might use, Word, maybe Python, or using R as a workflow component that plays nice with others. So I work for a company called Geosyntec. We're an environmental consulting firm. We're all over the world. We're all over the country. And we also have a lot of offices here in the Pacific Northwest. I'm up north in Bellingham, and we also have one here in Portland. And we have a lot of different practice areas. I'm on the data and mapping team in practice, where my colleagues do GIS and drafting, and me and my colleague, the data colleagues, we do database management, data visualization, and anything number crunching. And we support a couple of our practices, the environmental practice, which does a lot of contaminated site remediation, and then water resources that they look at water rights and water supply. So those are the type of projects that we're typically working on. So about me, I actually have a background in environmental science. I hesitate often to call myself an environmental data scientist, but that is what I do every day. I have a lot of experience in natural resources management, especially water quality. So that's kind of the perspective I come to data science from. And I fell in love with R. I got really excited about R and using it in my workflows when I was working in water quality, so I could speed up the time between collecting data in the field and then having it processed and being able to hand it off to my manager to make policy decisions about it. So I use things like R Markdown to make quick reports that was based on monthly monitoring data. And now I get to streamline workflows every day. So this presentation is a lot about R in consulting specifically, but this is really geared towards the beginners in the room or listening online. In consulting especially, we try to come up with creative and efficient solutions to problems that our clients have. And we try to be pretty platform agnostic. But the reality is I have a favorite tool. There is no secret. But I am careful to apply that tool when it's the right tool for the job. And for beginners out there, or maybe you're in a role right now where you would like to use R, but you don't really have a lot of opportunities, I want to talk about some examples of how you might introduce R to your colleagues or into your workflows or into your team's workflows to really make things more efficient. So there's no task that's too small for R. And I have found too in consulting, but elsewhere too, if you're not in a company that's already using R routinely, you might need to do a little bit of internal advertising to let people know what it is, what you can do, and how you as an environmental data scientist can be a really important member of the team. So I'm going to launch into a bunch of examples. First of all, no task is too small. Things like compiling or combining files, which is a very simple, easy thing to do in R. People might not know that that's actually really easy to do, that it is one way to get your foot in the door to help your teammates out, to say, hey, let me take your weekly downloads and combine those for you. Oh, let me merge these relational database tables for you for this summary thing you need. Here, let me pull this metadata and header info from your time series data sets. Here, I can make you some QC sheets that make sure that my code is doing what I expect it to be doing, and you can check my work. And then importantly, making Excel outputs, because reality is most people that at least that I work with, they're not going to do R. They want to have things in Excel so that they can do whatever it is that they want to do with their data afterwards. So we talk a lot about automating the routine, talking to, like, this is the advertising part a little bit. So in our data team, we talk a lot about to our colleagues, if you're going to do something more than twice, you should probably script that. And if you think that there's a better way to do something, there probably is. Come talk to me. So these are things, like the things on this list here are things that you're probably going to be doing in every project when it's an all R project, or if you're working on all components of a project. But these can also be separated out where maybe you're just responsible for the data wrangling piece of a project, and then you hand it off for the next steps. Maybe you're only doing QC or certain calculations or reformatting, just shuffling columns and making things into a set of valid values. And then of course, producing multiple outputs like those QC sheets so someone can check your work, summary statistics, the raw data outputs, whatever people need. And most importantly, plots. Who doesn't love the data visualization? I try to make plots for everybody. If they let me touch their data, I will send them a plot. I don't care if they don't want that, I'm gonna do it anyway. And they will hopefully look at them and be happy about it, because nothing beats a human's eyes on a data set. And most often the people that I'm working with are really familiar with their work and know what it's supposed to look like, or at least what they're expecting it to look like. So up here sorry, I'm bombarding you with a bunch of plots, but up here is an example in the upper left, is an example of type of plot that I like to do, which is like a QC plot, I call them. Like, here, check my work. I found some outliers based on this way that we're supposed to find and screen out outliers. Does this make sense to you? You can look at the plot as a person who doesn't do R at all and say, yep, Hanna, you got it right, or no, that one actually looks wrong. Sometimes people tell me they say, oh, well, I have, this is a really tricky plot. I need this specialty software that maybe we're paying for as a company to do this special thing. So down here on the bottom left is a Piper plot. It's a trilinear plot. It's looking at groundwater geochemistry. And of course, there's an R package for that. No problem. And then, of course, on the right, time series data sets where a project manager is at unknown intervals of time going to download data from somewhere, and they want to know right away what it looks like. So of course, we all know that this is a great opportunity to script that out, have R produce a bunch of plots, and in this case to do some really fun calculations like calculating evapotranspiration as the data set grows, and just update the plots. It's great this is a great example, I think, of like showing people this is the kind of thing you can do. Think about how quickly you can go from downloading that data to having something to show your client or show the project to. So I'm going to talk about some workflows too, where R plays nice with a bunch of its friends. So in our data group, we do a lot of database management. We use a database called Equus, which we use to manage and house our environmental chemistry data. It's a really great database, but sometimes it just needs a little bit of help. Our data workflow typically works that we get an EDD, an electronic data deliverable, from a lab with our analytical chemistry results. Sometimes it's in various different formats, whatever the lab can handle, and we can use R to clean that up, reformat, shuffle columns, fix our valid values so that it's really nice and easy to upload to our database where we can do other things with it. Our database does a lot of cool stuff, but sometimes there's calculations that it just can't handle, or updates that are a little bit more complicated to do, or like, I don't know enough SQL to be able to do it. So we can use R for that and feed that back, push that back into the database. Our database also makes really nice report tables, except if you want some special summary statistics or other things, and then it isn't really great for that. So we kick out a flat file and we run our R scripts to do calculations and stats. And then we can kick out those nice report tables or data visualization, or sometimes a flat file or a table that we are going to hand off to someone to do their special statistics in their separate programs, or to hand off to our GIS mapping team to put together a map figure for the project. So another example of R as just a component, we're right where it is the right tool for the job, was a project we did for the Upper Columbia Salmon Recovery Board. So the Upper Columbia River, the Columbia River there in Washington, the sub-basins that we were interested in are in that C curve in the middle there. And then on the left side is the picture of a floodplain. So this was a floodplain delineation project where a nonprofit, what they wanted to do is know where the floodplains are at different flood intervals. But there's data gaps and we have limited time, limited money, limited staff, limited accessibility. So how do we do that? And this is a GIS modeling and remote sensing exercise. So what we did for this client is we have this data pipeline where we start with a relative elevation model of the subbasin. We have discharge data for a specific stream or river reaches. We have a wetted area that we know the cross section of the stream or river at a given discharge for those reaches. And we read that all into R, where we have also gotten these cross sections based off the center line. And these are like cross sections that are about a foot apart. They're very frequent. And then we just iterate through using the R magic that this is where R is absolutely the right tool for the job. To fill that up, fill those cross sections up and find the stage height that then we pass on to GIS for them to generate a floodplain and then to calculate those metrics. And then we're prioritizing salmon habitat restoration. I think I forgot to mention that before. This is what it's for, salmon habitat restoration. So I'm going to talk a little bit about just the R component and like the details of it. So this pink line is that cross section that we pulled from the relative elevation model raster. We have the elevation of that cross section, and then we get this profile, which is the part we're interested in. So we trim off the ends beyond the two maximums on either side of the data set, so we can zoom in. This is what we're interested in. We don't care about the edges. I'm going to zoom in here just because. And then we start filling it in. Increment by increment, filling it in until, so this is the cross section that we're looking at now, filling it in until this area matches the wetted area for that given discharge that we're interested in. And then we do that twice for our, two flood intervals that we're interested in. And then we have these stage heights specific to the cross section at each 1 foot interval on these streams. And so then we feed that to GIS, and GIS turns it into a floodplain. Then we calculate our metrics. Then we do salmon habitat prioritization. Another example of a project that has R as a component, this time it's a little bit of a bigger component of this project, was the Metau Okanagan Beaver Project. This was a stream flow restoration project where our client was a nonprofit. They got some grant funding to install beaver dam analogs, so man-made beaver dams, and then they're monitoring stream flow, how it's changed, groundwater elevations, things like that. So we help them with a lot of data processing. So we have transducer data, time series data. So there are these pressure transducers that are in the water that are looking at how much pressure is above that sensor. So we know how much water is there. The 50-minute interval, their quarterly downloads, there's a couple years of data and 55 monitoring stations. And it needs a lot of processing. Each data set needs to have pressure compensation from air pressure. It needs to be paired with manual measurements so we can do the calculations to convert that pressure into a stage height or a water level elevation. We need to do a bunch of QC to make sure everything paired up nicely and is correct. And then we need to submit it to the regulator, which in this case was Department of Ecology in Washington. So the data pipeline for this is we have tons of Excel spreadsheets. So we have all our transducer data sets. We have all our barometer data sets. That's the time series stuff. We have those hand measurements of specific field forms that field staff are filling in when they go into the field. And then we have an inventory or crosswalk that we use to pair everything up. And so we read that into R and we're able to pair the data sets using time, doing all the calculations, doing a bunch of QC checks to alert us to maybe things not pairing up properly. And then we have to sprinkle in a little bit of Python. And the output for this was a bunch of QC sheets. This is where the human is the right tool for the job, because nothing beats a person looking at a plot and deciding whether this looks like it makes sense. There's times when the pressure transducers are frozen. There's times where there is no water there, and we don't want to use that data. So that is really easy to find visually, and not as easy to find by scripting it out. So the part where there's the sprinkling of Python specifically was for creating within Excel an Excel plot that then if you toggled like, oh, I want to exclude this data, your plot's going to change dynamically in Excel. I couldn't figure out how to do that just using R. So that's when, oh, I need a little help from Python. So if anybody in this room knows how to do something like that in R, please let me know, because I would love to know how to do that. And then once the human has QC'd everything, we can read that back into R, combine all those data sets, do some summary statistics, summary plots, convert to discharge, and then kick everything out that we need to for reporting and to the regulator. So takeaways from this presentation that I hope you get is that R is often the right tool for the job, but not always. Sometimes it needs to play nice with others, like Excel, especially when you're working on a big team, most of whom do not code at all. It really helps to be accommodating and be able to produce those outputs in Excel, which everybody knows is easy to do out of R. Also that there's no task too small. I think that that's important for especially beginners, or like I said earlier, like if you have a job where you want to be using R, but it's not really standard, or you don't have ways to use it yet, there's a lot of ways you can introduce R and build a lot of efficiency to your projects, even if it's doing a small component of it. And then sometimes it takes some internal advertising to let people know what's possible. And that's it. Thank you.
Thank you so much, Hanna. Yeah, I think we sit in a very unique position as data scientists and those working with data to really facilitate other people. So that's really great to hear about that. All right, now we've got Evan Landman talking about developing reproducible transit analysis in R.
Thanks so much. So yeah, I'm going to talk a little bit about R in the public transit field. And since I know probably most of the people in this room, maybe you interact with transit as a rider, or maybe a person with an opinion about it in your local jurisdiction. I'm going to talk a little bit about sort of what we do in the field of like public transit planning, the type of data environment we're working in, and the role of R for our team. And then I'm going to talk a little bit at the end about why we are an R-based organization and how we've sort of integrated R throughout our entire approach as an essential part of serving public transit agency clients really all over the country. So when we think about transit, I mean, the first thing that comes to mind is, that thing that maybe you sometimes take to get, take on your way to work or to meet a friend or to go to the store. But transit is also this really complex spatial process, right? It's schedules that determine when big, expensive vehicles move all over the region. It's hundreds of people that show up to work every day, all throughout the day at sites all over the place to get on those vehicles. It's the way that we interact with people on board, the sense of safety and comfort that we have on board the vehicle. There's sort of no end to the direction that you can come to this topic from. And so that makes it a really interesting place to work in data, right? Because there's almost like an infinite amount of data produced in this field, right? These vehicles are systems with tons of sensors on them that are recording data constantly. So this image here, this isn't just a stock photo of the image of the inside of a bus, right? This is the fare card reader on a transit vehicle. The fare card reader is where you tap your card when you get on the bus. That records your location, where the bus was at that time, the time that you tapped it. It's connected to your account. And so that's a system that we can use to understand the movements of people through the system. It's really it's one of the many sort of like potential inputs into our field that we're sort of constantly thinking about how to integrate into how we understand these things at a higher level. And so transit agencies are really like constantly looking to change their service, right? They're constantly thinking about how can we make things more reliable, keep you from getting stuck in traffic? How can we make it easier for people to use our service and attract more riders? And so our job is to support agencies that are looking to study the design of their network. So what are the routes called? How often do they run? Which days of the week are they operating on? And so if you've ridden the bus in Portland, Vancouver, Dallas, Houston, San Jose, Cleveland, many other places, you've probably ridden on a service that we've helped design or evaluate or improve. And the way that we do that is by delivering insights about what's really happening throughout the entire system to policymakers so that they can make informed decisions about how to address those kind of questions on the left. But transit planning is also political, right? Transit agencies constantly hear conflicting things from the public. everybody hates their service. Everybody hates it when their service changes, right? And here in the US, where most of our work is done, we also never have enough money to do everything, right? We're always leaving someone behind. We're always, we always don't have enough space in the morning on that one run that gets into downtown right before the 9 a.m. shift start time. And so when you think about like, how do we respond to like these kind of questions? Well, we have to think about what our goals are. And then we have to give transit agencies and their decision makers information that actually helps them understand what are the things that what are the actions that we could take that actually address the needs that we're hearing about from the public? So when we think about what makes transit useful, how do we get people on the bus? We're usually starting with the perspective of a rider or a potential rider. And of course, they're in a city full of places they could choose to travel to, jobs they could hold, places they could shop, friends they could visit. But in a given amount of time on transit, you can only get to so much of that, right? In 45 minutes, you can get to this area in this blob. We call this a travel time isochrone, right? It's a shape on a map that identifies the area that's reachable in a given amount of time using the system. And so when we think about those things together, we think about your access to opportunities. What are the opportunities that your community makes available to you that the system is actually connecting you to? Beyond that isochrone, if 45 minutes is a travel time budget that's relevant to you, you're less likely to choose to hold a job beyond that extent. You're less likely to choose to visit a store there. And there might be options that could enrich your life that are not really sort of feasible to you just because the system's not providing that kind of a connection. And so in our work, we spend a lot of time trying to understand what are the opportunities that are important to people and to quantify how different changes to the transit network could impact that travel time isochrone for people in a particular place or all over the place. Of course, these are data-informed questions, right? You start from the question of where do people need to go? Where are people, right? You think about where is it convenient or inconvenient to use transit? So thinking about travel time analysis and the connection between different destinations. When you're thinking about changes and planning studies, right? What could we do to make things more useful? And do the things that we imagine when we're planning actually translate to improve connections? How much would those things cost? How many more hours per day would we have to pay people to drive those vehicles? And ultimately, how would people be impacted? What's the distribution of benefits versus burdens? Are we distributing those things evenly through the population, or are there disadvantaged or marginalized people that are bearing the brunt of our changes, even if we're well-intentioned? So in a given project, right, this is a project of mine from a few years ago in Dublin. We asked these very concretely. This is a large university in North Dublin, Dublin City University, DCU. And part of this project was about improving the connectivity of the major educational facilities inside the region to more people. And so we can quantify, very clearly, like where can you get today? Where could you get with our set of changes? And how many people are in those different areas, right? So putting, almost 70% more people within reach of that university, that's a way of understanding we're actually expanding the capability of this system, the public transport network, to take people to one of the most important opportunities available to them, a major university that grants training and, and information for all sorts of things that enrich people's lives. And of course, on most of our projects, we want to generalize that across the entire region. So thinking about how can we take those kind of measurements and make them for samples that we take across geographic regions that could be dozens or hundreds of miles in size. Which areas benefit, which don't, whose access are we increasing, whose are we reducing? So in a map like this is something we do almost on every project. We've looked at the comparison of travel times and the number of jobs and other destinations reachable from the centroids of each of these little hexes. And we've compared them with the existing network with our proposal to help the decision makers ultimately understand what's sort of the balance of the change and where are those changes benefiting and creating burdens. And are there places where we've created negative impacts that we need to fix or that we understand as the unavoidable trade-off of making changes to a complex system in the context of limited resources? And of course, ultimately, these comparisons help us get to clear decisions, right? When we look at alternatives, what does one deliver versus another, and which of those do we ultimately want to put forward into a proposal? So transit planning really is inseparable from data analysis. An individual experience is only a tiny window into how the entire system works. You usually only write a couple of routes, and even somebody who's really interested in the system, it would typically take them months to sort of take a single trip on everything. As I said before, every vehicle is this massive collection of sensors, produces a ton of data. Here in Portland, every bus produces a breadcrumb every 5 seconds, right? You can do a lot with that information, but it's a lot to work with. We're at an interesting point in the evolution of data standards. They're coming along, but we still have a long way to go. And of course, every person that rides the system has an opinion about it. So there's sort of this complementary side of surveying and public engagement that has its own data process. And so for us, R is really essential, right? Because we work for clients all over the country. Agencies with 1 bus, agencies with 1,000 buses. And the capability of those organizations to do any of this kind of work themselves is as varied as the number of vehicles they're operating. So our goal is always to take the experiments and the things that we develop for the first time for the largest, most capable agencies and make them available to the smallest places we can, so that everybody has the benefit of insights that somebody in Dallas or New York City does. For us, every analyst who joins our team ideally is somebody that's had some training in R previously, and they all learn to work it at least to the level of running and debugging our templated scripts, because we really feel like there's, with the variety of contexts that we're working in, we are the standardization that our clients can depend on to understand things with the same language and practices that are being used in other markets. And the R ecosystem has great tools for transit analysis, particularly the work produced by the Institute for Applied Economic Research in Brazil. They have these great tools for working with some of the main data standards. And of course, over time, we've also developed our sort of own internal tools that are about standardizing the kind of unique and characteristic aspects of our approach. So almost anything you want to do with transit requires handling multiple large, messy data sets, right? They all feature time and space dimensions. Transit is inherently spatial. It's about vehicles coming at particular times at particular stops. And there's really only one standard that everybody uses, this thing called GTFS, the General Transit Feed Specification. That's the format that your transit agency gives to Google to help Google Transit and Google Maps respond to your trip requests. And so that tells you, when is the bus supposed to get there? That's the thing that every agency has, and then everything else is a complete mess. So, you need to have a pretty strong kind of set of exploratory tools to work on this stuff from jump, right? Transit is totally spatial, so efficient mapping is a crucial skill, right? I hate traditional GIS. I hate ArcGIS. I think those tools are just, for somebody that wants to explore a data set, it's always been this huge, gate to getting to, real insight. And so for us, we've tried to take as much of our work, as much of our spatial work out of those kind of closed systems as possible, and to train people to actually interact with things through, the GG Maps package, things like the leaflet package, so that they're kind of looking at things in a spatial dimension right alongside the kind of work that they're doing to just clean and understand the data sets. By the way, if anybody's looking for that old pipes cell in the bingo, it's right up there. You've now met somebody who still writes the old pipes. I can't get over it, sorry. Travel demand is essential, of course. Census and all the public data sets, that's kind of the ground truth that we start from. So, of course, tidy census and all the things around it are crucial. There's this package called Leader that this guy, Jamal Green, who used to be at PSU in the MERP program, wrote a few years ago. That's unlocked this whole world of job data that was previously only available in flat files from the Census Bureau. Over the last few months, we've become more and more familiar with NHGIS through the IPUMS R package, as the integrity of the census APIs has become sort of over and over questioned by the new government. And we're always working on our own tools for handling the sort of more granular proprietary mobile data sets. So this is sort of an example of this. There's this thing called Replica. It's a model of like every trip in every region of the United States down to the point. It's a activity-based travel demand model. And so it gives you a really, deep and, kind of over detailed picture of where people are going. And one of the things that we've tried to do is to create some tools for working with their outputs. That's a closed, expensive proprietary data set. Most researchers aren't using it because it's so expensive, but many agencies are. And so for us, getting outside of their dashboards and their standard views and being able to unlock some of that information for a kind of a deeper analysis has been really important in kind of leveraging the investment that our clients have made in that product. And for me, since early on, I'm a data table guy. Data table has always been my best friend because transit has a lot of analyses that just barely fit on the laptop, just because of the the kind of time plus space nature of the data you're working with. So ultimately, for us, it comes down to sort of 3 steps, right? Because of just the variety of places we work, the variety of the data environment, we're always experimenting. Different clients have different requests and their own messy situation when it comes to their data on ridership, when it comes to their data on reliability, and all of those things outside of those standards that that there's this huge ecosystem of vendors for. But I think Peter said this at the beginning. If you do something twice, right, you should figure out how to do it efficiently and generically. So for me, it's been really crucial to train all of our staff to understand things not as like an opportunity for them to explore, but as an opportunity for them to use a template and ideally, find the things that are broken and improve it. And to look back, at regular intervals a couple of times a year and to think, okay, what are the things that we've been doing more and more of that really need to be an internal package, that really need to have an owner and a person whose job is to understand that process, both at the kind of like our code level and at a higher level about what are we trying to communicate and methodologically, how are we trying to evaluate it. And so for us, this has kind of been an evolution over the last decade in becoming an organization that really started with sort of my and a couple of my colleagues just like writing our code as analysts, right? And as we did more and more of that, we realized like we think this is the right way to have an organization that works with open source tools that pays as few technology vendors as possible. And the way that we get there is by taking sort of the same approach every time and having our own internal processes that enable us to standardize so that no matter where we're working, whether it's 1 bus or 1,000 buses, we know that we have the tools ready to answer the questions that we know are coming. So with that, if you're interested in transit or learning more about what we do, or you work with like intensely spatial things in R, I would love to chat with you. Don't hesitate to reach out, and I'll be around at the end of the day as well. Thanks very much.
Wow, thank you so much, speakers. Those were very, very interesting talks. I think we have, a few minutes for questions. Does anybody have any questions for our speakers?
Thanks. This is a question for Evan about the transit metrics. I'm kind of wondering what are some of those core metrics that describe, connecting people to destinations and kind of balancing that to like the frequency if you make a small network. Just curious about what some of those main metrics are.
Yeah, in terms of access measures, so those are usually in terms of like the number of destinations reachable in different amounts of time. So an example would be like the median number of jobs reachable in 45 or 60 minutes, right? If you're talking about making comparisons, you might look at the change in the median, and then you might also look at the number of people experiencing a loss and experiencing a gain. You may also look at other points in that distribution, right? Often we'll like kind of plot the distribution of access with two different networks and understand sort of like how does that change between those two scenarios. There's also sort of more in-depth ways where rather than looking at like a particular time cutoff, you're looking at like all travel times and then applying like a decay measure based on that, based on whatever that travel time is. So that's kind of, I guess, just sort of scratching the surface. But for us, we think those kind of metrics that speak to like the level of mobility that the network is providing are kind of most important. There's also this whole other slew of things around just like the number of people boarding and the boardings per hour of service or per dollar that are kind of like the more, I'd say the more conventional metrics. But for us, we always try to focus on like what are people actually able to do with the service. That's kind of, I'd say, the hallmark of how I approach this.
Thank you.
Thanks. We have another one over here.
Yeah, thanks. My question's for Peter. So for Peter and the metadata that you mentioned you have crosswalks and definitions and other information that you're storing and using with your system. But I was curious, like how are you actually storing your definitions and crosswalks? Are those CSVs? Is it JSON? Is it some kind of YAML configuration file? I was really curious to hear more about like how you structure that part of your project.
Yeah, so there's the present state and there's the future state, right? But right now those are in CSVs that are imported, and eventually we want those to be stored in a repository where they can be a GitHub repository where they can be accessed easily.
Have another one over here.
Okay. My question is for Hannah. Hannah. Yeah. So Hannah, I was curious when you were showing how you have different components of your project in R, but not others. I was noticing, for example, the GIS and like component of your project. And have you thought about moving that into R? Or kind of more broadly, are more parts of your projects being coded into R as well?
Yeah, I don't want to take any work away from my GIS colleagues, but definitely like the trainings that I did yesterday about doing mapping in R is really exciting for me to think about at least speeding up that pipeline. Exactly, about like someone wants to look at a preliminary map. That would be a great thing that we could use R for, but then our report ready production, we could still do through the traditional GIS. I think it would be a long path to switching some of those workflows. But yeah, the more and more that we have team members who are using R and familiar with it, the more we're able to move into R, where it just works a little bit more smoothly rather than, say, relying on our database to do something, which it can do, does pretty decently, but R could do it better. So finding that balance of when do we rely on our current tools and when do we build new ones using R.
Thank you. Remember, ask your questions both virtually. If you're attending virtually, please put your questions into the Slack. Or if you don't want to stand up, that's also fine. If you want to put your questions into the Slack, that's perfectly acceptable. We'll ask. But it looks like we've got another question back there.
Well, I'm going to be that person. It's a comment, but I wanted to call out Hanna's photo, and we should make it a thing. Take your photo with the hex sticker from this year and then be a speaker next year and submit your headshot with a photo of last year's. Wow, it's so meta. But it's the first person to have ever done that, and I love it. So thank you.
Question over there.
Okay. Great. Hi, Nathaniel. Thank you so much to the speakers. So I think this question was primarily for Peter, but I think Hannah and Evan, you might have something to say to it as well. So I really, where is Peter? Oh, great. Hey, I loved the metadata approach. I've worked in some similar concepts as what you did, and I see a lot of similarities. So I really liked it. One thing I haven't heard yet from anyone is running into pushback from internal folks who might say either, maybe I don't want to use R, or more specifically, even if we use R, wow, you've got all these ideas for this metadata system and that's nice, but not really my cup of tea. I just don't know if that's something we want to go down. That's something I run into a lot. I used to be scared of the people who are really like slamming their fists on the table saying this shall not stand. That rarely happens in my experience. But kind of the, nah, not my cup of tea thing. And this seems like a big deal, but we got other ways to solve it. I'd love to hear from anyone on the panel. Have you run into that kind of lack of engagement, and how did you address it?
I think for our team, definitely it does come up. And there's a big difference between the way we're able to work on projects that are happening internal to our team and those that are happening, with the broader, but some of the solutions, are thinking strategically and thinking in terms of, I know what the eventual goal is and the workflow I want to build out. I'm going to build that modularly and slowly over a period of years, and then eventually present people with tools that make their lives easier, right? And part of that has been getting a Posit Team server up and running and being able to publish data products to it. But that's been a big piece of it. In terms of approaching that type of resistance, I tend to take the approach of, like water cleaves obstinate stone. We just have to be persistent because it's tough.
Yeah, I would say that I've come across a lot of pushback too. And I think my approach to it has been trying to add transparency, that I think that a lot of times the resistance comes from not understanding what is happening. Even just in database management, people hand us their data and then it goes into this black box, and then you need me to get it out of there. And so, finding those ways to like make the data accessible, being quick with turnaround, which of course incorporating R into those workflows is exactly what's needed in order to speed up that pipeline, but also coming up with those like the extras, the QC sheets that kind of show your work and those things so that the other people on the team can trust but verify, I guess, that what's happening in the R script is actually what they want or need to happen for the project. But yeah, I agree. It's been a slow convincing sometimes to get us environmental data scientists on board on a lot of projects, certain kind of projects. But yeah, I think we're getting there, and I'm excited to have learned more tools on how to do that here.
Yeah, I'll say, internally, I've been really mindful to like build our team in a way that like for kind of client facing project work, R is our first choice. But there are some things that still like I've never been able to crack. So like there were all these great presentations this morning about Quarto and all this cool reporting stuff so many of you do. Our clients don't ever want that. They want to fiddle with all their documents. They want to edit all the text themselves. They want to move around all the images. And even when we like sort of do little test cases like in sort of early phases of projects or like as like a memo as opposed to a final deliverable, that's something that I have just never been able to make headway on, despite like the many obvious advantages of having sort of something that's fully integrated with data and code. I think especially in the public sector, people are so ingrained to this like look at the Excel table, paste the Excel table into the Word document, send the Word document around to 20 people, get all the comments, reconcile the comments, right? And that's a way of working that is just like, I don't know that like from my perspective as a consultant, I can change that workflow. The only opportunities I have to touch that are in things that are like products that are not reviewed. So that's something that I'm hoping there's a sea change on in the future.
And then we do have one question from on the Slack. This one's for Hannah. When you talked about QC sheets, you mentioned showing the outliers, but what other types of info do you typically include with those?
So I like to include, like the simple examples that I showed, just like merging data together. I do a lot of that because it's such a huge time saver. So one of the kinds of like QC sheets I do that are like to make sure that everything's pairing up correctly, that like this ID is translated into this. Is that what you meant? This is the units that I'm using. Is that what you wanted or expected? So the project manager can kind of look through and at a glance see, okay, here's what got read in, here are the dates and the summary, information about the data sets, and then to see if anything's missing. I do things like, dealing with analytical chemistry data, it's CASRNs. CASRNs are like the number code for chemicals, dealing with that and translating those properly. So having those sheets that check like, here's a weird one, make sure this is real, a real pairing, those kinds of things. So I kick those out into Excel so someone else can review those and kind of QC me without having to review my script. Those are some strategies I use.